For those just logging in, we'll wait about a minute to get started today. Okay, why don't we go ahead and start? Welcome to the Air-Sea Fluxes from Space webinar series. Today, we're fortunate to have Jennifer Waters from the UK Met Office, who's going to talk about investigating the impact of assimilating satellite total surface current velocities in global ocean forecasting systems. And I think this is work that is the result of a collaboration with multiple institutions and looking towards future satellites. So take it away, Jennifer.
Yeah, thank you. So this was an ESA funded project called the ESA ATSCV project. And yes, it was a collaboration by quite a few different partners listed here. Accurate forecasts of total surface current velocities are really important for lots of applications. So that might be search and rescue operations, ship routing, tracking of marine plastics and pollutants, and in a coupled forecasting application. But direct measurements of the TSCV are currently not really available with global coverage. So we have HF radar measurements in some coastal regions and acoustic Doppler current profilers making in situ measurements with limited spatial coverage, mostly in coastal regions and the tropics. And we can infer surface currents or near surface currents from the Global Drifter Programme. But due to this limited availability, we don't presently assimilate ocean current observations in our operational system. So this project was investigating the potential impact of assimilating satellite TSCVs in global ocean forecasting systems using observing system simulation experiments. And the key aims of the project were to provide supporting evidence on the usefulness of the data for future satellite missions, to test our data assimilation methodology and our capability to assimilate this type of data, and to provide feedback on observations requirements for satellite providers. For this study, we used two operational global ocean forecasting systems in a set of coordinated OSSEs. So that was the foam system that we run at the Met Office, and then the Mercator Ocean International System. And I believe that Elizabeth Remy presented last week on some work that they've been doing for the Odyssey OSSEs with the Mercator system, but this work sort of preceded that work. And today I'm going to focus primarily on what we did and the results from the Met Office system. So in our observing system simulation experiments, we're assimilating synthetic observations generated from a nature run, which is a high resolution free running model. And the observations are simulated with realistic observation errors from the nature run for all standard data types, as well as new observations expected from a skim-like satellite mission. And I'll just point out now that we also use the nature run as our truth, so we can use it to assess the outputs from the OSSE experiments. So just talking about the synthetic satellite TSCV observations that we're using, we were using observations from a skim-like satellite. So the skim concept, in the skim concept, the main instrument was a K-band conically scanning multi-beam Doppler radar altimeter and wave scatterometer. And it was making measurements over a 270 kilometer wide swath and 6 kilometer footprint. So I should say the skim satellite at the time of the project was one of the proposed satellites. Obviously that one hasn't gone ahead, but the project used this setup for the experiments. And the velocities from this satellite would be representative of the top 1 meter of the ocean. In our our experiments, we assimilated the 2D TSEVs along the skim swath, and those were provided in zonal and meridional directions. And the data was simulated using the Skimulator tool. And this plot here shows an example of the type of observation coverage that we get for one day, or would get for one day from a SkimLight satellite. So this is for this 22nd of January. Yeah. So now just talking a bit about the kind of observation errors for the skim data, and also the processing of the observations. So the 2D currents are constructed from radial currents using an optimal interpolation method with a 20-kilometre length scale. And this process introduces a mapping error, which is approximately 3 centimetres per second. So all of the TSEV observations that we assimilated contained this mapping error. And then the resulting currents that we got out from that had about 5 kilometre, well, had a 5 kilometre resolution both across and along the track. So in addition to this mapping error, the Skimulator also produced an instrument error for the TSEV observations, which was provided, which was dependent on the position across the track. This figure here shows the instrument error averaged along the track for one cycle of the skim satellite, and the blue shows the eastward component of the instrument error, whereas the orange shows the northward component. And you can see that the errors in the eastward direction are largest near the nadir, while the errors for the northward component are largest at the edge of the swath. And these plots here just to show a snapshot of what the instrument error looks like along the swath over the Atlantic during one day. So some additional processing we did for the Met Office experiments was that we thinned the data across and along track by 20 kilometre, that's a 20 kilometre resolution. And the reason for doing that was partly to reduce overfitting, but also to remove some of the correlated observation errors that we might expect to be introduced by the optimal interpolation method. Okay. So now I'll just give a bit of an overview of the Met Office foam system that was used in these experiments. So we used NEMO 3.6 for the ocean model, and that was at a 1/4 degree horizontal resolution with 75 vertical levels. And that was coupled to the SICE ice model. For data assimilation, we use NEMO-VAR, which is a 3D VAR at first guess at appropriate time scheme. And we use a 24-hour assimilation window. The state vector is temperature, salinity, sea surface height, zonal and meridional velocities, and sea ice concentration. And an important aspect of the NEMO-VAR data assimilation scheme is the multivariate balances, which are prescribed through linearized balance relationships. And these allow correlated background errors between different variables. So if you have a temperature observation, and you assimilate that, you'll also make corrections to the salinity, sea surface height, and velocities. So from the perspective of this project, probably the most important aspect of that multivariate balance is that we use geostrophy to specify the velocity balance. And finally, we use an incremental analysis update to nudge the increments into the model over a 24-hour window. So the standard objects that we're assimilating are satellite and in situ SST, altimeter, sea level anomaly, in situ temperature and salinity profiles, and satellite sea ice concentration. So this table is just summarising the main differences between the way the Nature Run is set up and the Met Office foam system is set up. So there are differences in the model configuration or version, the resolutions, and we use different wind current coupling coefficients. So 50% was used in the Nature Run and 100% in the Met Office system. Different ice models, fluxes, and actually we use different restarts as well. And then obviously the Nature Run is free running, so no data assimilation, whereas the foam system is using NEMO-VAR and is assimilating these observations generated from the Nature Run. So these differences should simulate realistic errors in our experiments and make it therefore relevant to the real world system. And it's possibly worth pointing out that this nature run was the same one that was actually used in the Atlantos project OSSEs. So it was assessed for its realism in this paper. So I'll just give an overview of the experiments that we actually ran. So we had a control experiment, which just assimilated the synthetic standard observations, so SST profiles of TS, sea surface height and sea ice concentration. And then we had 2 experiments assimilating the TSEV data. In one of the experiments, we assimilated the TSEV data with just the mapping error, and that we refer to that as the TSEV no error experiment. And in the second experiment, we include the mapping error and the instrument error in the TSEV observations, and that one's referred to as the ATSEV instrument error experiment. When I talk about the results, I largely focus on this second experiment because it's sort of closer to a realistic setup. And our run period was the 21st of January 2009 till 31st of December 2009. So these 2 grey boxes sort of highlight the sort of key differences in the way the 2 experiments are run. So in the control, there is no assimilation of velocity observations, but we do still make adjustments to the velocity through the balance relationship, which, as I said before, is geostrophic. And because it's geostrophic, there's no velocity balance at the equator. So that means that we don't make any direct adjustments to the velocity fields at the equator or near the equator. In the TSEV assimilation experiments, there are both balanced and unbalanced increments produced for velocity. And then the geostrophic component gets transferred to the other variables through the balance relationships. So when you assimilate a velocity observation, it gets separated into a geostrophic and an ageostrophic increment, and that geostrophic increment gets balanced with the other fields. As part of setting up the TSEV assimilation experiment, new background error covariances were defined for unbalanced U and V, and new representativity observation error variances were estimated for the sea surface U and V. So now I'll show some results from our experiments. So I'm going to start by showing the impact on the surface velocities. So these root mean squared, we were able to calculate root mean squared errors between the 25th of February to the 31st of December relative to the nature run. And then these plots here are showing the difference between the root mean squared error in the ATSEV instrument error experiment and the control. And so where you see blue, that indicates that the root mean squared error is smaller with the TSEV assimilation. So we can see that the largest improvements are generally in the western boundary currents, the ACC, so the Antarctic circumpolar current, and then in the equatorial region. And globally, we saw a 23% improvement in the root mean squared error. We do see some degradations in the middle of the gyres for zonal velocities, and I'll come back to that in a couple of slides. So we also looked at the impact on the surface velocities in the forecast. So we ran 7-day forecasts every 7 days. And then these plots are showing the forecast root mean squared error as a function of forecast lead time. So the blue line is the control, and then the green and orange show the 2 TSEV assimilation experiments. And what I really want to show here is that the improvement that we see in the global velocities is really well retained over a 7-day forecast. And actually, I think we get a 4-day improvement in forecast skills. So quite a nice improvement, not only in the analysis, but in the forecasts. We also did some Lagrangian assessments. So particles were seeded globally at a 1/4 degree resolution and then propagated for 6 days from the 9th of September using the model daily analysis velocity fields. And then the separation of the particles from the nature run were calculated on each day. And this plot is showing the percentage of the particles within 50 kilometers as a function of advection time. So the control is in blue here, and you can see that after 6 days, less than 70% of the particles are within 50 kilometres in the control. But when we have the TSEV assimilation, that increases to, I think, just above 75%. So we get a nice improvement in this Lagrangian prediction as well. So that's given a bit of an overview of the results we got in the surface. And so now I'll move on to talk about some of the impacts in the subsurface. So looking at subsurface velocities. So these are similar to the plots that I showed before. So they're the difference in the root mean squared error from the experiments with the TSEV data and the control. But now they're calculated at 220 meters. So the top plots are where we have the instrument error in the TSEV data, and the bottom is where we have we don't have the instrument error. And on the left, you have the zonal velocities, and on the right, the meridional velocities. So the largest improvements are very much in the ACC at 220 meters. But we do also see improvements in the western boundary currents and in the equatorial region, particularly for the zonal velocities. We do see some degradations in the tropics, and these are largely in regions where there are complex salinity structures like the Amazon outflow. So we think this is probably because the prescribed multivariate balances are not really appropriate in these regions where you've got complex density structures. And also we see in the zonal velocities, this degradation in the middle of the gyres that we saw at the surface. But interestingly, I've shown the plot here where we didn't include the instrument error because you don't really see it in these plots. So we think that this is largely due to kind of a low signal to noise in the observations in these regions. So I think we need to improve observation error specification in this area so that we don't get this impact when we have low signal to noise in our observations. Now these are root mean squared error profile plots for zonal velocity for the global region, the full global region, the equator, and the South Atlantic western boundary current. So globally, we see that the root mean squared error is improved down to at least 1,500 meters. So again, the blue is the control, and orange and green are where we have assimilated the TSEV data. And you can see that if you look in the South Atlantic western boundary current, for example, there's a very deep improvement with the TSEV assimilation. But if we look at something like the equator, we can see that the improvement is more restricted to the top 300 meters of the water column. Now I'm going to look at the impact on some of the other variables, so temperature, salinity, and sea surface height. So these are similar plots to the ones, again, I've shown before. So again, blue shows improvements with the TSEV assimilation relative to the control. And for SST on the left and sea surface height on the right. The SST, again, it's mostly and the SSH, it's mostly the ACC that's improved, and then the western boundary currents. And the global improvement in the SSH was 14%. So that's to the RMS error, and the global SST RMS error was improved by 6% with the TSEV assimilation. And these plots at the bottom show the profile root mean squared percentage improvements relative to the control for the two TSEV assimilation experiments. So we can see that for salinity, there's improvement throughout the water column. When we include the instrument error, the improvement is near the surface and then sort of below maybe 100 meters for temperature, and throughout the water column without the instrument error. So overall, we got some really good improvements with the TSEV assimilation, with the vast majority of our metrics showing some kind of nice improvements when we include the TSEV data. But I wanted to focus a little bit now on the impact of the TSEV assimilation on ageostrophic velocities. So now I'm looking more at some single observation results. So we took a single innovation and we calculated the increment, which is shown here on top left. but also the balanced increment, which is calculated, which is the top right. So this is just the geostrophic component of the increment. So you can see that the balanced increment is generally a bit larger. It's got kind of a wider spread, whereas this the geostrophic increment has this dipole structure, is a bit smaller. So what we did was we ran two experiments, one where we applied the total increment to the model and one where we applied just the balanced increment. And below is the model response for those two experiments. So it's the model response after the end of the IEU followed by a 24-hour forecast. So I think what you can probably quite clearly see is that the model response in both cases, it looks really similar. And actually, it essentially just looks like the balanced velocity increment. So that really implies that the ageostrophic or the unbalanced component of the increment isn't really being retained in the model. So we wanted to have a bit of a think about this and why this was happening and whether we could improve this. So away from the equator and boundaries, near inertial oscillations are a large component of the ageostrophic velocities. So localized winds changes cause near inertial oscillations in the ocean currents at the inertial period, and that's about 24 hours at 30 degrees north and 14 hours at 60 degrees north. So we apply our increments to the model using an incremental analysis update. So we nudge them in over 24 hours. And we know that actually this dampens near inertial oscillations in the model response. There was this recent paper here which showed that when the near inertial oscillations are spurious, this dampening effect is very useful. But it does have the impact that it restricts our ability to correct near inertial oscillations when we have valuable information about them. So for example, if we have total surface current velocity observations. So still looking here at single observations, but now looking at a kind of time series of response, the time series response. So this is the model response to a single ageostrophic increment in the northwest direction valid at 12 hours. So that increment is represented by this cyan arrow here. And in this top panel, what we did was a direct insertion of the increment. So we could compare it to the IEU. What we actually did was we took the increment and then rotated it by the inertial period so we could apply it at 0 hours. So the increment that we actually applied is this green one here. And then we just applied that to the model and looked at how it responded. And what we got with this was these blue arrows. So this is the model response. So you can see the near inertial oscillation in the model fields when you add that increment in. Now the middle panel is showing what happens when we do an IEU. So in this case, we're nudging the increment in throughout the time window, throughout the 24-hour IEU, and that's sort of represented by these green arrows here. And the blue arrows show the model response. And so what you can see is that the model is trying to rotate, but there's a cancelling effect because you're constantly applying this increment in the original increment direction. And so what you actually get at the end of your IEU is quite a small model response, and the model response isn't really in the direction of the original increment, and it's not really in the direction of where it would be if you'd done a direct insertion either. We've sort of proposed like an alternative, which is actually to do a rotated IEU, and where you apply the increments, but they're rotated at each time step by the inertial period. And it might be a bit small to see here, but in this case, the green arrows are rotating around throughout the 24-hour period. And now the model response, certainly in terms of direction, looks much more similar to the direct insertion case. So we think that a rotated IEU has the potential to be able to initialize near inertial oscillations in the model with the phase and magnitude of the unbalanced ageostrophic velocity increments. And so we did do a couple of experiments to try and look at this. So it's quite, for a 3D VAR system, it's quite difficult to actually implement this, because to be able to do this, you really need to know the time the increment is valid for, which isn't really how 3D VAR is designed. So to get around this, what we did was we calculated a time of observation analysis, and in order to do that, we made sure we wanted to get rid of any crossovers of the data, the observations throughout our assimilation window. So we did that by only using the descending tracks and below 60 degrees north and south. So this plot here shows the tracks that we're left with if we do that, and the colour is the observation time in days. And then we calculate a time of an observation analysis from that. So we're basically just assimilating a filtered data set so that we avoid any crossovers, so that we can calculate our time of observation analysis, and then we can apply this rotated IEU approach correctly. So we ran a couple of experiments to test this. These were just run for a short period between January and the end of March 2009. So in the first case, we used just these filtered observations with a standard IEU. And then the second experiment was using the same observations, but now with a rotated IEU. So what we found from this was that there was little impact on the total surface velocity root mean squared error. But we did see a larger impact if we looked at the residual root mean squared error. So that was a root mean squared error of the sub-daily variability. So we calculated that by taking the hourly velocities and minusing the daily means. So these plots show the percentage improvement in the residual surface zonal velocity root mean squared error for the northern hemisphere at the top and then the southern hemisphere at the bottom. So the picture is really mixed. The blue line is the standard IEU and the orange is the rotated IEU. And the picture is really mixed in the northern hemisphere. So we're not seeing a benefit from using the rotated IEU here. However, we do see some small benefit in the southern hemisphere. And these results are just being shown for March. So it's quite likely there's a seasonal, there might be some seasonal reason why you might see improvements in the southern hemisphere and not in the northern hemisphere. I think this is something that we plan to do some more work on in the future, because I think it's quite important for us to be able to exploit more information out of the ageostrophic component of the velocities. So at the beginning, I mentioned that these OSSEs were part of coordinated experiments that were done with the Mercator system. So I'm just going to give a bit of a summary of the results from the Mercator system. So generally in these type of studies, it's important that you have evidence from multiple, so at least 2 forecasting systems. And that's because the impact is usually very dependent on the details of the model, the data assimilation, and the other aspects of the forecasting system. So comparing the Mercator system with the Met Office system, we use a different data assimilation scheme. They use a seek filter, we use 3D-var. They're using a 7-day assimilation window compared to our 1-day assimilation window. So there are various differences which might impact the performance. So I just wanted to summarize the types of results that they'd got from their experiments. So the Mercator OSSE showed some good improvements to surface velocities with the TSEV assimilation. So the root mean squared error was reduced by 12% in their experiments. This figure here is showing the same Lagrangian results that I showed earlier, but now the black lines are showing the results in the Met Office system and from the controls for both the Met Office and Mercator system, and the orange shows the results from the ATSEV instrument error experiment. So you can see there's generally a relatively similar impact by day 6 on the spread of the particles. In the Mercator system, the impacts on sea surface height were quite small, so only about 3%. And they did see some degradations to temperature and salinity and also to subsurface velocities. And they felt that some of the results might be improved by reducing overfitting of the TSCV observations and applying vertical localization to avoid any spurious vertical correlations. One of the other findings was that their multivariate balances are possibly less constrained by geostrophy than in the Met Office system, and could potentially allow some ageostrophic balances. And that's because the multivariate balances will be dependent on an ensemble in their system rather than prescribed by the kind of linearized balance relationships that we use. So now I'll just do some conclusions. So just to summarize the results from the Met Office OSSEs, we saw some significant improvements to global surface velocity root mean squared error statistics with the TSCV assimilation, with a 23% improvement in the root mean squared error and a 4-day gain in forecast accuracy. And the largest improvements are in the western boundary currents, ACC and equatorial region. So one thing I wanted to mention is that the improvement in the ACC with the TSCV assimilation is partly so good because we have actually relatively poor performance of SSH assimilation in this region. So we found that the TSCV assimilation really compensated for the poor performance in the altimeter assimilation. We also found that subsurface velocities were improved down to 1,500 meters in the western boundary currents and 300 meters near the equator. And we found the TSCV assimilation is able to make significant improvements to the subsurface geostrophic velocities, which particularly produces good improvements in currents in the eddy-rich regions, like the western boundary currents. So global temperature and salinity were also improved at most depths. And because geostrophy is used to define the velocity balance, that part of the TSCV signal, due to errors in the geostrophy velocity, are projected onto those variables to produce that benefit. So we did see some degradations in the middle of the gyres where the signal to noise in the TSCV observations is low, and also degradations in the tropical regions where we have complex salinity structures. But we think that some further tuning of background and observation error variances should go some way to improve results in these regions. And I've shown that away from the equator, the improvements are largely due to geostrophic corrections. So the ageostrophic increments are not very well retained in the model, and this is an area for further work, I think. So yes, looking at limitations and future work. So these are idealized experiments, and not all the processes were represented in the simulated TSCVs. So for example, our nature run didn't include tides and Stokes drift and the submesoscale processes. Also, the full error budget was not included in the skim observations, and in particular, the correlated observation errors that we might expect from a skim-like satellite weren't included. But there is some ongoing work at SURFAX to include correlated observation errors in NEMOVAR, and this should help to give us the capability to deal with these types of errors in future experiments. I've said this before, but I think it's really important that we better exploit corrections to the ageostrophic velocities in the Met Office system to really gain the full benefit from velocity assimilation. And also in this work, we assimilated the 2D currents, but possibly we could assimilate the radial currents, which would remove that optimal interpolation step, and that would reduce the overall errors in the observations that we had. And finally, we could improve the velocity control variables used in the data assimilation. So we use sonar and meridional velocities in our control variable, but we could use potentially use velocity potential and stream function so that the variables are less correlated. And there's some work ongoing at Reading University to look at this possibility. So as a final conclusion, the study demonstrated that we have the capability to assimilate simulated satellite TSCV observations, and that they have the potential to significantly improve prediction of the ocean state in global ocean forecasting systems. And I like to think that the results from this study should support the case for future satellite missions with TSCV observing capabilities. And also, I've just left here this table, which was in one of the papers that we published, which provided some requirements for satellite TSCV observations for use with global ocean prediction systems. So I'm not going to go into detail, but those are there if you'd like to have a look. Right. So thank you for listening. And there are a few publications that have come out from this project. So if you're interested, you can, I guess, find out some more information from these. Thank you.
Thank you so much. Questions?
I might stop sharing if that's okay.
Yeah. Maybe I'll start by, while people are thinking of questions, I'll start by asking, you pointed out that you thought your results might have been, for the one aspect of this might have been affected by the fact that you've done the simulation in, you got a better southern hemisphere response because the simulation was done in sort of January, February, March. Do you have a sense of what the mechanism might be behind that?
So we wondered if it might be associated with mixed layer depth. So perhaps that you might have quite a deep mixed layer depth in March in the northern hemisphere, and that might. I think there was some papers that suggested that maybe the kind of energy flux that you get into the near inertial motions would be less if you have a deeper mixed layer depth. Though we thought that might explain why that was. But I think it would be really helpful for us to look at a later period actually, and sort of really, or a different period of the year, and or extend those runs to sort of see if we see some actual seasonality in them. It was kind of a hypothesis of why it was the case in one hemisphere and not the other.
So you felt like from what you had, there wasn't enough information to fully diagnose it.
Yeah, possibly not. I mean, generally the strength of the near inertial oscillations was much stronger in the southern hemisphere during that period, because we did look at that. So we did some spectral assessment where we looked at that. Yes, but yes, it would be. I think we would like to have a look at sort of an extended period at some point.
Great. I see that Ben Storer has a question in the chat. Ben, do you want to go ahead and just ask?
Oh, sorry. I can read. I could read it if.
Yeah, that's great. Yeah.
So, and the question was, I didn't quite follow how to interpret the percentage of particles within 50-kilometer plots. Could you explain a bit on that, on what those are and what we should expect? Okay, so what we did was we seeded particles at quarter degree resolution on a quarter degree grid, basically, and then we used the daily model fields to project those particles. For both, we did it for the for our TSCV experiments, so our RSSE experiments, but also for the nature run. And then we looked at how far apart the particles had drifted from the nature run ones. So on each, so with where all the particles for each experiment, the particles were starting in the same place, and then we're looking at how far after one day the nature run particles would have drifted from our OSSE experiments, and then the diagnostic we used to kind of interpret that was how many of those particles were within 50 kilometers. So just to give you some sort of summary statistic, I guess. I hope that made sense.
Yeah. Ben says it makes sense and he has no mic. So. Roger Samuelson has his hand up.
Thanks, Jenny. Really nice talk. I can't, unfortunately, I came in a few minutes late, so you may have covered this, but I wondered what exactly was the definition of the surface velocity in the model? What exactly is it? And then also similarly, how do you decide what the ageostrophic component is?
Okay, so the velocity in the model, do you mean in terms of when we're doing the data assimilation, or more in terms of the assessment?
Well, I guess just the definition. I mean, suppose it's probably the velocity in this topmost grid cell in the model.
Yes,
Is
yeah,
that
that's
right?
right. Yeah, so
And
it's sort of top 1 meter is, I think, what
1 meter. I see. Okay,
yeah.
great. Thank you. And then
Um,
for the geostrophy, I just wasn't sure how you decide what that is. I mean, what you subtract.
um, so the geostrophic component is estimated. Well, we have an estimation of what the balance should be from the background field. So it estimates the geostrophy from. So we take a set of background fields from the beginning of the assimilation cycle, and it estimates. It uses that to estimate the geostrophic part. I'm not sure if I'm explaining this very well.
Well, I think I
Part of
understand it. It's basically the uncorrected, the unadjusted, the state without the increment is used to define what the geostrophic velocity is, and then the part of the increment that is uh, somehow not in balance with that geostrophic. I mean, it probably doesn't matter that much because the velocity doesn't change that much in the increment, but I was just curious uh, because we don't
yeah.
really know what the geostrophic component of that increment is, it seems to me, unless you already know what the adjusted SSH is, say. But
Yes, I see what you mean. Yeah, I
yeah,
mean, it's
so
all
if you did
done.
something with an iteration or something, it would be slightly different, but it probably doesn't really matter because the adjustment at any one time step is probably quite small compared to the geostrophic component.
Yeah.
Yeah, okay. All right, thanks.
Tony Lee has his hand up.
Hi, Jen. Thanks for your
Hi.
very nice presentation. I have a question. Whether UK Met Office has a plan to move towards couple assimilation that can leverage the simultaneous measurement of current and wind, for example, to better handle many things among them, like
Good question.
NIO? Yeah.
So sort of talking about a fully coupled data assimilation, I guess. I don't think that's in any short-term plans of ours. But it's an interesting point, because actually, if you don't, it probably would make velocity assimilation a lot more effective if you were also correcting the wind simultaneously. So I agree that that might be a way that you get more impact, perhaps, say, out the ageostrophic component of the correction.
Yeah, but it's a big effort, fully couple assimilation.
Yes, yeah. It's not. I don't think it's in our near-term plans.
Right, and given that fully coupled assimilation is quite some time away in the horizon, is there any method that could allow the addition of surface wind or wind stress as a state vector? So expanding, it's probably not going to be 3D WAR. I don't know, maybe it is possible with 3D WAR. Basically, you add it as a state vector and include the error covariance as well. Still, force ocean assimilation, is there a possibility?
Oh, yeah. I mean, again, I don't think it's something that we plan to look at, but that's an interesting idea. Yeah, I mean, I actually didn't say this, but perhaps slightly less relevant to this community, but we were surprised by how well generally the velocity assimilation worked.
Yeah.
And so actually our plan at the moment is we're trying to
leverage that first.
Yeah, so what we're trying to do at the moment is we're looking at assimilating the global drifter derived velocities, because that would be, but once we get that working, that gives us some more possibilities, I guess, to kind of tune the velocity assimilation and try and get the most out of it.
Yeah, that makes sense. Yeah, thank you.
Other questions? Maybe I'll ask one more. The satellite swath width looks like it's not too wide, and so it must take a week or more to get a full global coverage. Have you pondered what would happen if you had a wider swath? And I guess conversely, you showed the performance which degrades on the edges of the swath, and so did you consider just assimilating the high performance part of the data?
Well, I think it depends on whether you look at the zonal or meridional part, because I think the zonal part is worse actually at the middle of the swath. So which
Yeah.
we didn't consider filtering the data anymore. So a colleague of mine has done, in the same framework, did some experiments looking at the wide swath altimeter data, so wide swath altimeter data comparison to increasing the number of nadir altimeter observations. And we definitely found, I know from an SSH point of view, because we use a 24-hour simulation window, that sometimes he found that there was better impact from having more nadirs than there was from having the wide swath, but just because of the repeat cycle. Yeah, that's a good question. I mean, I think that the repeat cycle on the skin was about 12 days, and I think it was giving about 80% coverage over 4 to 5 days, which given that we saw sort of quite good impacts out to 7 days in the forecasts, meant that we could still quite well use that information. So yeah, I don't know. I mean, it would be interesting to look at that, and but I guess maybe, I don't know if you have, you might have a bit of, maybe you might, I don't know how the errors vary with wider, if you have a wider swath, whether you get, like you said, larger errors, or yeah.
I think it all depends on resolution too, because
Yeah.
you can beat down some of the random error by averaging over larger cells.
Yeah.
But yeah,
But
so for example, the Odyssey concept has a 1,500 kilometer wide swath, and so, but with similar performance issues on the edges of the swath. And so then you get
Okay.
almost daily coverage, and that's a different kettle of fish, maybe.
Yeah. Okay. Yeah, and I mean, we were using, for us, we prefer to use a so we used, there were options with the optimal interpolation method of different resolutions. We used the lowest the lowest length scale for the smoothing, because we wanted the kind of highest resolution product for our system. But, yeah.
But you used the data effectively at 20 kilometer resolution.
Yes, yeah, we filtered it to, yes, yeah, we filtered it to that resolution in the end.
Well, I think that's what would be probably usable velocities, something around that, with even with
and although
swath.
I think, so did I say it was 270 kilometers? I think the swath on skim. I don't think that actually the data that we used was as wide as 270 kilometers. I think the data that we actually were using for the 2D currents, I think, was provided over a shorter, over a narrower range. So.
Yeah. Okay, well, are there other questions today? If not, this has been really wonderful. Thank you for a really great talk, for going through these amazing results.
It's nice to share them with you. Thanks for inviting me.
Thanks
you,
so
Jen.
much.